back to chapter 2. Today we're going to be looking at section 5, which is all about the complex zeros and the fundamental theorem of algebra. There's not really much new in this section that we didn't already cover in the previous couple sections. So that's kind of nice. There's just that one little twist at the end, which is barely even a twist. So our learning targets today: write factored polynomials in standard form and identify zeros and x-intercepts. Find polynomial functions with given zeros. Match graphs of polynomial functions to lists of zeros with their multiplicities. Find how many complex and real zeros polynomial functions have. And find all zeros and linear factorizations of polynomial functions. So a lot of these should sound very familiar because it's what we've been doing. So let's take a look. We have a couple big theorems going on in this section. The first one is the Fundamental Theorem of Algebra. Bum, bum, bum. Um, Generally speaking, when in math, when something sounds like big and complicated like that, it's actually not that complicated. It's when things sound really easy that's when they get complicated. So the Fundamental Theorem of Algebra just says a polynomial function of degree n has n complex zeros, which could be real and non-real. And then some of them may be repeated. So if you have a fifth degree polynomial, it will have 5 zeros. It might be the same zero 5 times, but it will have 5 zeros. That's all that says. The linear factorization theorem. If f of x is a polynomial function of degree greater than 0, then f of x has precisely n linear factors. Well, if it has n zeros, then yes, it has n factors. Where a is a leading coefficient, so you can factor out a, and then you'll have all the factors. Some of them may be repeated, some of them may be non-real as well. So you could have like x plus 2 minus I. That's a linear factor. So it just says that you can split it up into x plus or minus a number for however many degrees it has in the polynomial. The fundamental polynomial connections in the complex case. So this is just a update on the synonyms that we had for, roots, zeros, solutions, x-intercepts, all those things mean the same thing. Well, for complex numbers, when we have non-real numbers, we still have some. It could be the solution. We still call it a zero because it's what makes the function zero. Or x minus k is a factor. What we don't have, roots and x-intercepts. We don't have those because those complex, the complex roots we get with things like this, where they don't cross the x-intercept. And so, or the x-axis, so there is no x-intercept, and that's what a root would imply. So when we're talking about the complex solutions, we just don't usually refer to them as roots or x-intercepts because it just doesn't make sense in context, even though they are actually the same thing. So, and then another theorem, the complex conjugate of zeros. What this one says is that if you have a complex number that has a conjugate, then its conjugate is also a root. And so if 2 plus 3i is a root, then 2 minus 3i is a root. If negative I is a root, then positive I is a root. The complex conjugate, we change the sign of the imaginary part of the number to get that. And how that happens is our complex conjugates come from the quadratic formula. X equals negative b plus or minus a square root b squared minus 4ac all over 2a. So when we had the irrational roots, we also had their conjugate because of that plus or minus. If this doesn't simplify out, we had an irrational root. If that number inside of that square root is negative, we'll have a complex root, but that plus or minus still stays there. And that's generally how we find the complex roots. It's from the quadratic formula. That's all it is. The only other way we generally find the complex roots is if we end up with like x squared plus 2 equals 0. We can subtract the 2 and then square root, but when we do square root both sides, you still get that plus or minus. So we always have the complex conjugate as a root. And what that means is that complex roots come in pairs. So if we have a 7th degree polynomial, it could have 7 real roots, or it could have 2 complex and 5 real, or it could have 4 complex and 3 real, or it could have 6 complex and 1 real. And so the complex roots always come in pairs. So finding a polynomial from given zeros, we've done this with non-complex roots. So if we have x equals 1, 1 plus 2i, and 1 minus I, our polynomial f of x, it could start out as 0 equals, we have x equals 1. So that means that x minus 1 is a factor. We have 1 plus 2i, so we have x minus 1 plus 2i is a factor, which means we also need x minus 1 minus 2i. Now, before I get that last one, so that's the complex conjugate, we had to have both of them. Before I put the last couple up, you might be thinking like, wait a second, you being me, did not distribute that negative sign in either of these two. Distributing that negative sign, all that's going to do is make this first one x minus 1 minus 2i, and the second one x minus 1 plus 2i. So basically, I just switched the order of the two factors. You get both of them regardless, so you don't even have to worry about that distribution because you're going to have both of them. And the same thing here, we could have x minus 1 minus I and x minus 1 plus I. So this is the polynomial in factored form. A lot of the times it's going to tell you to find the polynomial in standard form, which just means we need to multiply this out. We're going to have a 5th degree polynomial because we have 5 roots. And when we multiply them out, I would multiply out the complex number with its conjugate first, because that'll get rid of your imaginary numbers. So f of x, there's the pen, equals x minus 1. And then we'll take the first two. So we'll have x times x is x squared. And then we have to distribute everything. So x times negative 1 is negative x. X times negative 2i is minus 2i x. Then the negative 1 times x is minus x. Negative 1 times negative 1 is plus 1. Negative 1 times negative 2i is plus 2i. And then the 2i times x is plus 2ix. 2i times negative 1 is minus 2i. And 2i times negative 2i is going to be negative 4i squared. Now, that we'll simplify this in a second, but remember that I squared will end up being a negative 1. So that goes away, and that just becomes plus 4. All right, and then the last one, I'm going to put it underneath. That's just what we'll have to do here. X times x is x squared. X times negative 1 is negative x. X times I is plus ix. Then negative 1 times x is minus x. Negative 1 times negative 1 is plus 1. Negative 1 times I minus I. Then the negative I goes to negative x, so negative ix plus I, and then minus I squared, but minus I squared is going to be plus 1. All right, so now we can do some simplification here. So we have f of x equals the x minus 1 is still there. And then let's see, we have an x squared. We have everything with I should cancel. So we have a minus 2ix plus 2ix. That goes away. We have a plus 2I minus 2I. That goes away. And so what we have left here, we have a negative x minus x. So that's minus 2x. And then we have a plus 1 plus 4 will be plus 5. So we have x squared minus 2x plus 5. And the other one, we have an ix minus ix goes away. We have a minus I plus I goes away. And so what we have left, we have an x squared. Minus x is minus 2x. Then plus 1 is plus 2. So now we have those guys, which is polynomials, which we still need to multiply them out, but that's it's getting there. I would definitely be taking this in steps. Don't try to do this all at once. For our two, let's multiply together the two quadratics first. So we'll have x minus 1, and then times, I'm going to stack these. It helps with multiplication if you stack them. We're going to have x squared minus 2x plus 5, x squared minus 2x plus 2. We're going to multiply. So we have 2 times everything, so this will be 10. Negative 4x, 2 times x squared is 2x squared. Then we'll multiply by negative 2x, so that'll be a negative 10x plus 4x squared minus 2x cubed. And then multiply by x squared, so we have 5x squared minus 2x cubed plus x to the fourth. We can add all this together to get x to the fourth minus 4x cubed. 911 plus 11x squared minus 14x plus 10. That goes right up into our equation. So we have x to the fourth minus 4x cubed plus 11x squared minus 14x plus 10. And now we need to multiply these out. So this could stack again, but since x minus 1 is just a binomial, we don't need to. But, let's stack it actually. We already have it right down here. Let's just go from here. So let's go x minus 1. No, I don't have enough room below that. Never mind, I was not thinking. Actually, no, I only need 2 rows. Yeah, that'll work. We'll just write small. X minus 1. So multiply by the negative 1 to get negative x to the fourth plus 4x cubed minus 11x squared plus 14x minus 10. Then multiply by an x, we'll have 10x negative 14x squared 11x cubed negative 4x to the fourth and x to the fifth. Now we can add these together. I'm going to add them together and put them over here. So we have an x to the fifth. Negative x to the fourth minus 4x to the fourth is minus 5x to the fourth. 4x cubed plus 11x cubed is plus 15x cubed. Negative 11 minus 14 is negative 25x squared. 14x and 10x is plus 24x minus 10. So that is what that polynomial would be in standard form. So is that kind of a long and obnoxious process? Yes, it is. Yes, it is. You shouldn't have to multiply out too many of them, but you will have to multiply out a few of them. The multiplication is just practice multiplying. The big part of this part of the topic that's new is this step, specifically getting your pairs of conjugates. That's the key to that. So that was writing the polynomial from the zeros. This one's going to be finding the zeros. So we have a polynomial. We have f of x equals x to the fifth minus 3x to the fourth minus 5x cubed plus 5x squared minus 6x plus 8. Sometimes it'll give us a root to begin with. Sometimes it'll give us a complex root. If it does, use synthetic division, divide out that complex root. We need to get it down so that it's a quadratic, because once it's a quadratic, we can deal with it. A quadratic or something like a quadratic. This one, it doesn't give us any information, so knowing the rational root theorem, we know that any rational roots are going to be factors of 8 divided by factors of 1, which is the leading coefficient. So it could be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. So that gives us a few things to try. We can use strategies to help us narrow that down. For instance, we could graph it. Here it looks like we have a root at 2, 1, and 4. Negative 2, 1, and 4 are all possible roots. That's going to be my first guess. So let's start with negative 2. And then we have 1x to the fifth minus 3x to the fourth minus 5x cubed plus 5x squared minus 6x plus 8. Going to bring it down. Multiply, get negative 2, add is negative 5, multiply is going to be 10, add is 5, multiply is negative 10, add is negative 5, multiply is 10, add is 4, multiply is negative 8, add is 0. Hey, look at that. Negative 2 did in fact work. All right, how about 1? And then again, we have to start with our answer there, because now we don't have a fifth degree, we have a fourth degree. We're paring it down to be a polynomial, or to be a quadratic. So just looking at the graph here, you will not be able to find those complex roots. You have to whittle it down. So if you discovered in the past that, oh, hey, I can just look at the graph and find these things, I don't actually have to do the synthetic division, put in the work, you are sorely mistaken, because that was just practice for this. So we're going to do it with 1. Bring it down, multiply, add, multiply, add, multiply, add, multiply, add. Hey, look at that. 1 works too. All right, now let's go with 4. Oop, I was a little bit low there because I can use the answer. So we bring it down, multiply, add, multiply, add, multiply, add. So 4 works. And now what we're left with here is x squared plus 0x plus 1. And we need to get that to equal 0, because that's what we're finding. We're finding when f of x equals 0. So those ones worked. Well, here's where we could use the quadratic formula, or we could subtract, so we get x squared equals negative 1. square root x equals plus or minus root negative 1, which is x equals plus or minus I. So here would be our 5 complex zeros. We could write that in factored form if we needed to, if that's what the question was asking. F of x would equal x plus 2, x minus 1, x minus 4, x minus I, x plus I, all multiplied together. So that gets us what that factored form looks like. So we've been doing this. The only difference is right down here, we get x squared equals a negative number. We get the square root of a negative number. And that just becomes that imaginary number. It becomes I. And then we deal with that. It's really no different than if it was an irrational number, except that you can't look at the graph and have it find the intercept for you, and you get a decimal that you wouldn't get credit for anyway. So it's all basically the same. I will see you in class, but until then, keep working problems, keep asking questions, and as always, happy mathing.